I'm extremely proud to lead Lawrence Livermore and to be lucky number 13 and to be a card-carrying member of the national security community at this moment. And thank you, Paul, for your comments. This has been a very sobering reminder that nuclear security is still very salient to our national security, and the work that my lab, Los Alamos, Sandia, and many of the other laboratories do in support of these missions and directly in support of the effort in Ukraine is incredibly important. So I hope that we're able to get through to a better place, and I wouldn't have asked for this way to have this very important civic discourse on this really important topic, but it really has opened many people's eyes to the state of the world today. So with that, I'm going to start by giving you a little teaser on the big event that we had at Livermore recently. And so if we can show the video, and I apologize for the dramatic music. At the end, that's the best part. So this story, the story of how we got to this amazing science accomplishment, really is a great arc to tell the story of what national labs are and what they do and the important role they play in the U.S. science and technology ecosystem. So I thought I would do three things. I'm going to talk a little bit about my lab, what it is, what we do, sort of put it in context for you. Then I will tell the story of how we got to that amazing result, despite, many people believing it was not possible, which is the best part. Okay, maybe not the best part, but it's a good part. And then at the end, I'm going to talk a little bit about what it means for the future. And so, this is a foundational building block for what could be a very exciting inertial fusion energy future. And so I hope by the end of this, you'll know a little bit about the labs and appreciate the role we play, a lot about inertial confinement fusion, and then get super excited about fusion energy for the future. So as was mentioned, Lawrence Livermore National Lab is a national security lab. I like to describe us as a national security lab with a nuclear core. So we were founded, last year was a big year in many dimensions. Last year was our 70th anniversary. We were founded in 1952, quite literally to be the counterculture to Los Alamos. So the Los Alamos came out of the Manhattan Project, having built up all this expertise around nuclear weapons technology. The nation was in a Cold War with the Soviet Union to really build up our own arsenal, our own national security posture, and it was realized that a closed ecosystem is not very healthy. And so you needed to build a counterpoint to the research and development that was going on at Los Alamos, where you could have another cadre of scientists who understood all this information and could provide a technical challenge. So Livermore was founded with that as its founding premise. There are a few other unique attributes to Livermore at its founding. So the first major procurement that Livermore made was for a supercomputer of the day. So computing has been at the heart of our laboratory since our inception and plays an incredible role in this journey. And the second component is experimental science. really pushing the boundaries of what's possible, working at a scale and level of complexity that many other institutions would have a hard time managing. And that's a unique feature of my lab, but also of the national labs in general. So the lab was founded to push the boundaries and immediately went into the nuclear weapons development program, went to Nevada to have their first nuclear test, and it didn't work. And we know it didn't work because it was a tower shot, and the tower was still there after the shot. That's a bad sign. We had lots of diagnostics, but the tower was a bad sign. So the Livermore team there's a very iconic picture of that. There were two experiments, the Ruth and Ray experiments. Livermore didn't, put that away and ignore it and pretend it didn't happen. We took that picture, and it hangs in a conference room to this day in the nuclear weapons program called the Ruth and Ray room. And so that's the original origin of the Livermore chip, which is another feature of us. We were the second lab. In the old days, we used to say we were the Avis of the nuclear weapons business. We try harder. But the lab was built around this concept of unbounded technical ambition. So our founding fathers were Edward Teller and Ernest Lawrence. Lawrence brought big science down from Site 100 out into the flatlands in Livermore. And that really was the founding principle of our laboratory. Take on very big, very complex challenges and use very multidisciplinary teams to work on these really hard problems. So the laboratory recovered from that, and soon after our founding had one of our biggest successes. So in the early days of the nuclear weapons program, nuclear weapons were very large, very heavy, and could not be credibly carried on anything other than really large missiles or in airplanes. And the Navy decided they wanted to get into the nuclear weapons business. And so the challenge was set. Could you make a weapon, a warhead small enough and light enough that it could fit on a missile that could fit in a submarine? And so Edward Teller took this challenge and then went back to the lab and told the lab what he had done. I took this challenge. We're gonna, shrink nuclear weapons in weight and scale by, order of magnitude. And that became the iconic first success of Livermore, the Polaris program. So the first nuclear weapon that went to sea on a submarine came from Lawrence Livermore. The irony of this is that we're now an Air Force lab. I don't know, somewhere along the way we lost the Navy. But that project was completed from the initial challenge to deployment in 4 years during a nuclear test moratorium. So when we look at the challenges we have today in advancing our national security capabilities, I tell this story a lot because we have demonstrated in the past that with limited knowledge, limited capabilities, but really hard work and dedication, we can make things happen on a very fast timescale. And the world today really demands that kind of ethos. So Polaris set us on our track to today. And that nuclear weapons enterprise, that collaborative frenemy relationship we have with Los Alamos is alive and well. We work in very close partnership, but challenge each other technically in many, many areas. But if I look at my lab, again, national security is our mission. Nuclear weapons by budget is about 2/3 of the laboratory, so our budget's about $3 billion. But that includes a whole range of foundational science, technology, and engineering capabilities. And our job is really to understand the biggest, most complex problems facing the nation and use our capabilities, our people, our tools, our ideas to tackle those big problems. And so over the arc of our history, we've expanded into a huge range of mission spaces. Early in our history, we began working in biology. Initially, that was to study the health effects of radiation on humans. Today, that's grown into a very significant program in computational biology as an example of how these things spin out. Early in our history, we created the first global circulation models. Again, nuclear weapons are large, complex multiphysics problems. The climate is a large, complex multiphysics problem. So the computational infrastructure we had built was very applicable to that problem. And that was during the 1950s. So we've been in these businesses for a long time. I told one of my colleagues who questioned why we're in the biology business, we have been doing biology since before there was a nuclear nonproliferation treaty. So some of the missions that people associate with our laboratory didn't even exist at our inception. So if I look at the national security space, that definition is very broad in my mind, because there are many things that contribute to our national security posture. I believe strongly that science and technology leadership is a key component of U.S. national security. And so U.S. leadership, visible leadership in key science and technology areas that our adversaries can measure really tells them something about our capabilities. So we work in nuclear weapons, we work in threat reduction across all spaces, so chemical weapons, biological security, nuclear nonproliferation, and nuclear radiological security issues and explosives. And we run very unique facilities. So we have something at the lab called the Forensic Science Center. It does operational support to law enforcement and the intelligence community, and it's one of 2 labs in the US that is certified to support the Organization for the Prohibition of Chemical Warfare, for example. We also run something called the National Atmospheric Release Advisory Capability, NARAC. NARAC does plume modeling, very sophisticated plume modeling with a specialization in nuclear incidents. So for example, when the reactors were impacted at Fukushima, that center operated 24/7, providing planning guidance to the Japanese government to help them understand what the evacuation zones needed to look like. So we can draw on our expertise on things nuclear or chemical or biological and bring them together with this operational focus. The third area, and one that's getting a huge amount of attention lately, is climate and energy security. Again, we have long expertise in climate modeling. For us as an applied science laboratory, the real question isn't, is the climate changing? The question is, what are we going to do about it? So we have huge capacity to understand what these changes are going to look like, what communities and regions are going to be facing. How can we use our tools and our engineering prowess to bring technologies out into the field to begin to help people mitigate the effects of a changing climate and adapt to the changes that are already underway? We also do a huge amount of work on civilian infrastructure. For example, understanding things like cybersecurity of the grid. Cyber physical systems are very complicated, and our infrastructure, as you all well know, was built long before cybersecurity was a thing. And so there are many issues and concerns about the kind of threats that our infrastructure face. Although the team that does that work briefed me for the first time, they have a program to really understand what all the potential threat vectors are for a cyber physical system. And they were explaining to me what the threats are, common threats are to the grid. And they said, well, the most common threat to our energy infrastructure and the grid is squirrels, because they crawl into transformers and die, and it's really a big deal. And because of that, they named one of their tools Squirrel. And so every time they brief me, I ask them what they're doing about the biggest threat to the grid, and we have not solved the squirrel problem yet. I don't know. I mean, we have lasers. You could put lasers on something. I don't know. No joy on the squirrels. But they have done interesting things like try to apply ideas and methodologies from collaborative autonomy to things like rooftop solar arrays. So if you want to do something nefarious to a group of houses that are all producing energy, instead of being able to penetrate the system at a central node, you'd have to take over a number of the elements of the system before you could have a mass effect. So getting those elements to collaborate instead of using just a master controller at the center. So interesting nexus between security and some of these other technologies. We're also doing a big focus right now for the Department of Energy is place-based innovation and regional partnerships. The department also just received something like $80 billion to do deployment of energy technologies. So we've been working in partnership with our Livermore Lab Foundation with the community around Bakersfield, which is an oil and gas community, to help them think through how to go through an energy transition in their community. One of the big concerns in the community is that there have been many promises made to community members about technology transitions and from some of the big industrial players in the arena, so there's not a lot of trust. So our foundation has developed a lot of educational materials on technologies like carbon capture and sequestration. And there are many industrial players who are interested in doing a carbon capture demonstration in that region Turns out spent oil and gas fields are a great location to think about sequestering carbon under the ground. We have a lot of experience with underground subsurface science from our nuclear test history, and so we've long been working in the CCS game. So we're trying to build very unique types of partnerships, community actors, governments, local educational institutions like Cal State Bakersfield and the community college system, help them build their expertise and capacity, and then working with industrial partners, try to get a meaningful demo going on CCS, as an example. And then the fourth pillar in our security space is really around what we call multi-domain deterrence. It's all the other defense domains that you might consider. So space, cyber, directed energy, conventional munitions, hypersonic weapons. And what we try to do is find places where we have unique skills and capabilities that can be applied in these arenas. So for example, in space, we've long had a history in space science because we have a lot of expertise in optics, because we build big lasers. And I'll come back to big lasers in a minute. But because of that expertise, we've been able to develop very novel optical components, small monolithic optical components for small monolithic telescopes, as an example, that you can put on small satellites to get very interesting and high-fidelity imaging off those platforms. We also did things, though, like we developed the first laser guide star, again, using our understanding of adaptive optics and lasers, which is what's used on ground-based telescopes to correct for atmospheric aberration, and really drove a revolution in ground-based astronomy. So the other key feature of how we work is this synergy between open science. You know, most of the people, the ideas, the innovation is going to happen outside the fence line of the laboratory. I have 8,000 people. That's just, statistics don't work any other way. So we participate in that community. That ensures that I get the best people in my laboratory, that they get to test their skills, they get to have real careers and publish, and build their reputation as scientists and engineers. We bring those tools, those capabilities, those new ideas back into our national security programs, and then we make sure that our national security programs have the ability to take advantage of the best tools and capabilities and modern cutting-edge science. It gives us a view into what the world is doing, what the trends are in technology, what the areas are that are strategic for the US, what we should be worried about, and where we should really be leaning in. And it allows us to help the government understand what the key technology areas are that they should be concerned about paying attention to. You can imagine what's on the list for the government at the current moment. They're worried about things like AI and machine learning. They're worried about hard technologies like accelerator technology, where we have unique skills and capabilities in the US. Increasingly, things like fusion, which has its origin story comes out of the national security community. And for inertial confinement fusion, that really is the focus of our program. But it has this obvious other benefit. So how do you balance the benefits and risks of research in these sort of dual use arenas? So that's, if you look across those four pillars that I described, nuclear security, threat reduction, climate and energy security, and multi-domain deterrence, that sort of captures everything we do. It's built on a foundation of fundamental scientific research across key disciplines. So the nuclear weapons mission tells us what kind of big facilities and tools we need. It tells us what kind of people we want, what disciplines we steward, but they really are applied across this very broad space. More recently, we did an exercise where I asked the senior management team 2 questions. The first question was, what are the biggest, most important challenges facing the nation or the world for which we have something unique to offer? And the second question was, what's the biggest impact we could imagine having if we weren't kidding? Like, we're going to really do this. Through the whole of lab, we are going to invest, we're going to build partnerships, we're going to build bridges. And so we created 4 what I'm calling mission focus areas around these key questions that really drive the work that we do. For anyone who follows the effort underway in the US to recapitalize the nuclear weapons infrastructure, the first mission focus area is around stockpile and enterprise transformation. How do you build an enterprise and a deterrent that's salient to today's threat environment, which is very different than we anticipated 30 years ago. The second one is around biology. We started about 10 years ago working in partnership with industry, clinical researchers, and academia to apply high-performance computing to really speed up the development of drugs and therapeutics. That was a really good idea. It was very hard to get people to invest in it heavily, not because it wasn't a good idea, but it didn't feel urgent. It feels substantially more urgent today. So we have made very significant contributions along with our colleagues across the national lab system to the response to the COVID pandemic. But today we have very significant programs going with the Department of Defense, who's very worried about resilience, force resilience, and rapid development of therapeutics and countermeasures for either emerging threats or engineered threats. So that's area number 2. How do we make the U.S. resilient to emerging and pandemic disease? The third area is this climate adaptation and mitigation. I think this is actually a really big deal and a place where we could have a very significant impact. And then the fourth area, the Department of Defense has created a new vision for how they want to operate called integrated deterrence, bringing all the instruments of power across the government and all the domains together in new ways to achieve asymmetric advantage. That is about the entire description of the integrated deterrence rubric that exists, because it's very complicated. How do you think about operating in an environment with, using Ukraine as an example, these major conflicts start with low-level skirmishes that may not even look like bad actors are involved. It may involve cyber attacks, but not against military targets, against civilian infrastructure. And then they escalate, and then you have to worry about nuclear coercion, which has been a really disappointing and frightening part of the conflict in Ukraine. I never thought I would see the day when a nation would shell a nuclear facility in a conflict. I mean, it's just been extraordinary. So we're really trying to help think about what kind of tools would you need, modeling tools, systems analysis, wargaming, to really think in this very complex multidimensional space. How would you think about different technologies coming together? And then getting our technology communities together to understand what kind of game-changing new technologies or approaches do we have that could really be beneficial. As you can imagine, in addition to the Ukraine conflict, the Department of Defense is spending a lot of time thinking about the Indo-Pacific. If you think about the region that the commander of Indo-PACOM covers, it's like half the world. It's mostly water. Projecting force is not a simple exercise in that environment, and we have lots of vulnerable bases, and they're worried about things that range from, how can we make sure that our energy infrastructure will work when we're isolated, to how do we get the capabilities where we need them, when we need them, in less than, weeks to months of deployment. So super exciting, lots of, really big problems to tackle, lots of focused effort in the government to make these next technologies go along, and then lots of incredible science going on. So we're in the midst of a huge revolution in our capabilities. This year we'll take delivery of El Capitan, which is the first exascale computer for national security applications. El Cap will be over 2 exaflops in capability. Very excited to have that hit the floor. I remember 20 years ago when we hit the first 100 teraflop machine at our lab. Our design community, first of all, when it came, they were like, we don't want this computer. I don't know what I'm even going to do with it. And within a year, they were telling the computing folks, you can't take one of my cycles away because I can't do anything without this computer. So we understand many things that exascale computing will enable, but I think we've only just scratched the surface. And coupling that with large-scale efforts in AI and machine learning, which are really changing the way we think about how experimental data and high-fidelity models and simulation come together, there's just going to be an explosion of knowledge and advancement over the next few years. So super exciting. The second big scientific advancement area for us has been additive and advanced manufacturing and materials. Again, bringing computing, design optimization, active control and correction together with new technologies to really change the way you think about making stuff. And it's incredibly enabling. I mean, building technologies that would not have been possible a decade ago. And we're working across many material areas and in partnership with industry and academia, again, bringing communities together to really advance the state of the art. But the big story is, of course, what we've been doing with our big laser, right? So I'm going to switch gears a little bit now and tell you the story of the Inertial Confinement Fusion Program as an example of how we have stewarded a technology area over many decades to achieve amazing things against significant odds, I would say. So 60 years ago, shortly after the invention of the laser, it was postulated that maybe you could use lasers to create the conditions in the laboratory that would allow you to ignite a fusion capsule. So at that point, modern thermonuclear weapons use fusion, and the sun obviously uses fusion, but short of those really extreme environments, there was no conceivable way to get that kind of fusion environment in the laboratory. So the lab embarked on what would be a very long journey of science and technology that took many twists and turns along the way, and I think opened new fields of study in ways that we really didn't anticipate at the beginning. So that original postulate suggested that if you had a 1,000 joule laser, 1 kilojoule, you should be able to achieve fusion ignition in the lab. Well, in one dimension, that was probably true. So we don't live in a one-dimensional world, it turns out. So the lab began building larger and larger laser systems to begin to systematically study the physics of that process. And I showed the video so you could see the picture of the target physics and what happens. So the way we study inertial confinement fusion, we use a can, a gold can, typically, that has a hole at either end. In the current configuration, we shine 192 laser beams into that can, so half the beams into one side, half into the other. They interact with the gold and create X-rays. That very uniform bath of X-rays then impinges on a little capsule that's at the center of it. Historically, they've been made of many materials. Currently, they're made of what we call high-density carbon, what you call diamond. The outer surface blows off, and then by the rocket effect, that pushes the inner surface in. In the center is deuterium and tritium, heavy hydrogen fuel. That gets compressed. If you can compress it fast enough to a high enough density and hold it together long enough, it will ignite and burn the fusion fuel. So that's been the quest for these 60 years. Can you make this process work at a laboratory scale with a laser of the scale that we have today? So as the knowledge progressed and the modeling and simulation tools became more sophisticated and we had more experimental data, several things became very clear. One was that you had to have a particular wavelength of the laser in order to avoid a very bad effect where a lot of hot electrons would be produced and they would impede the ability of the capsule to implode. So the way to make a lot of laser energy is to work at long wavelengths. So in that case, working at 1 micron wavelengths, infrared wavelengths. And so it was clear that wasn't going to work. You would have to frequency convert that light to a shorter wavelength to mitigate that effect. When you frequency convert, you lose a lot of the energy. So this was the first thing that makes it harder, because now you need a much bigger laser because you're going to have this loss mechanism at the beginning. The second thing is this target has to be very precisely built. It has to be very smooth, because any little bumps on the surface of the target, when the target is being imploded, will grow. They'll grow into big ripples, and if any of that material gets into that hot fusion fuel, it cools it off and turns the fusion off. So that's the second thing. The targets have to be marvels of precision engineering. The target has to be round when it implodes. So you have to have a very uniform target that's very precisely specified, and the laser energy has to be delivered really accurately so that you don't push the target in one direction or the other. And the last thing is you have to be able to get the laser energy into the can. So I sort of glossed over one of the hardest parts. When you shine the laser light into the can and you generate the X-rays, you also blow the surface of that gold can off. So the little can starts to fill with gold plasma. Gold plasma is essentially a mirror for laser light. So you have another race. You have to get the laser energy in before that gold plasma fills enough of the can that it starts reflecting the laser energy out. And by the way, when it reflects the laser energy out, it goes back down the laser beam lines and burns holes in them. So it's a very bad very bad thing. So in the 1980s, we were on the path to build a 20-beam laser called NOVA. NOVA was going to be about a 200 kilojoule laser, so we learned a little more energy was going to be helpful. But calculations had improved enough that it was determined that that would not be enough energy to ignite a capsule. So the decision was made to not make a 20-beam laser, but to make a 10-beam laser for NOVA. So that's actually where I started my career as a postdoc, was doing experiments on the NOVA laser. It was an amazing facility. So it was about a 40 kilojoule laser, and the team working at that facility really laid the scientific foundations for what it would take to get to an igniting capsule over many years. The National Academies in that period did a study because the lab wanted to build the next laser, the bigger laser that would really get us to ignition. And the goal was to build a 10 megajoule laser because everyone felt very confident if we had 10 megajoules, we can make that sucker ignite. And that was probably true. However, going from 40,000 joules to 10 million joules was deemed too big a technical step. So the decision was made to split the difference and aim for a 2 megajoule laser, and the idea for the National Ignition Facility was born. It's also in that period where the US ceased nuclear testing and the Stockpile Stewardship Program was born. So we always took care of the nuclear deterrent by doing modeling and simulation, high-fidelity experiments, and using nuclear test data to benchmark our models. In this era, we would not be allowed to do nuclear explosive testing, and so we needed a new set of high-fidelity capabilities to really dig in on the physics. And the cornerstones of that were a new hydrotest facility where we could do surrogate experiments, which ended up being DART at Los Alamos, computing that was many thousands of times more powerful than what we had at the time, and in 3 dimensions instead of 2. That eventually led to that 100 teraflop machine, and now on to exascale. And then the National Ignition Facility. And the first great mistake of this program was calling it the National Ignition Facility because it had the deliverable right in the title. So that really focused everyone's attention. By this time, we had learned, though, that these lasers could produce conditions that are really interesting for studying materials, hydrodynamic instabilities, radiation transport, other things that we care about for understanding the science of nuclear weapons. So we created a new field of study, really, called high energy density science that was aimed at really understanding these extreme conditions and what you could, the kind of physics that proceeds from them. We also got the astrophysics community interested because we could create conditions that look like the kinds of conditions you see in the universe, like the center of giant planets or in supernovae. So we created laboratory astrophysics out of that. And an entirely new pursuit in material science with these extreme conditions. So many thousands of times, millions of times above atmospheric pressure conditions you could create really unique states of matter. But NIF was built to be a stockpile stewardship facility and to really create that last cornerstone of science, understanding the physics of thermonuclear burn that would allow us to not return to nuclear testing. So the journey began. It took till groundbreaking for NIF was in 1999 era. I did the very last shot on the NOVA laser. I remember it vividly because it was June of 1999, like a week before I had my second son. So there's great pictures. I was great with child when we did that last shot. But the decision was made to shut down NOVA so we could build the next facility. When the project was approved, 7 of the core technologies required to make the facility work did not exist. Right? Not like nice to have features. Things that absolutely were required to make a facility at this scale work. So large-scale plasma switches that would allow us to manage laser beams that were going to be this big in aspect ratio. Those crystals that you use to convert the light from infrared to green to blue would take decades to grow with traditional techniques. So we had to figure out a new technique to grow these crystals. Actually, a scientist came from Russia who had a new technique and managed to grow all the crystals we needed for the facility in several years instead of several decades. So the leap of imagination, the commitment of the government to this project is almost inconceivable today, the level of risk that we took on. Every one of those technologies was successfully invented and deployed in this facility. So in 2009, we turned the laser on and began the National Ignition Campaign. So the laser was meeting all its performance specifications, 1.8 megajoules, and we began target physics in earnest with a goal of achieving ignition within the first 2 years of the life of the facility. So if I could have my slides, I'm going to show you some charts, just some brief charts. Okay, I have a clicker. Am I pushing the wrong button? There we go. So way over here, that's National Ignition Campaign. You may notice that you can't see on this scale, you can't see the data points. Now, it turns out it's not very hard to make fusion reactions and make neutrons. So we've been doing that for a long time. But we were producing very small amounts, so nearly 2 megajoules of laser energy and 2 million joules, 2.5 kilojoules of fusion yield out. So this was very disappointing, very disappointing. And there were many problems that were learned because we had done such an immense scale up in the regime we were working in. We learned many, many things, like plasmas are hard and they're terrible. Never do anything with plasmas. So we had plastic capsules. It turns out that the type of system you had to use, laser pulse you had to use to drive a plastic capsule made this plasma mirror problem in the whole room much harder because it was a long pulse and there was a lot of reflected energy. We were using gas in the whole room to hold off the walls of the whole room. That gas turned into plasma and it became a problem in and of itself. So a lot of work, massive team of people working very, very hard, failed to achieve ignition. I mean, the major conclusion of the National Ignition Campaign, which ended around 2012, was we never really got much past those several kilojoule yields. We did, however, learn which of the levers needed to be pulled and controlled better to move to the next step. So a new team was brought in, the counterculture to the counterculture, to do a different approach. They tried to create a capsule design and laser pulse design that would be very stable to those hydro instabilities I described. And they knew the yields would be lower because they weren't going to be as ambitious in how they pushed the capsule, but they figured if we can turn off this mixing problem, maybe we can make some progress. So immediately, we start to learn. Now we're at 25 kilojoules. Everyone's feeling a little more optimistic. Still, pretty distant from target, but, the learning is going in earnest. And what we learned is an old lesson of science, right? The best science comes from challenging your own ideas, right? So having these two groups pursuing different approaches and challenging each other was really helping us learn faster and move more quickly. And we also deployed a boatload of diagnostics in that era so we could really see what was happening in these targets. So if we started with the idea that we would succeed easily, we didn't need many diagnostics. If you ignite one of these capsules, it turns out it's very easy to tell. You get a lot of neutrons, everything gets very hot. So many diagnostics, much learning, 25 kilojoules. Then we decided we would look at different target materials. So our material science and target fab people who are geniuses. I mean, they've made things happen that are unbelievable. That little can is about 1 centimeter long. The little target inside it is 2 millimeters in diameter. The fill tube that goes into that target to put the deuterium in it is 2 microns in diameter. So it's just an extraordinary achievement, and it has to be cooled to cryogenic temperatures. So we shifted from these plastic targets to this high-density carbon target because you could use a different shaped laser pulse that would be more favorable for getting the energy in the laser, and you didn't need that gas that was screwing things up. So when you had the HDC Bigfoot, now we're at 55 kilojoules, and we're really feeling good. We're learning. We're doubling our yields every several years. So progress proceeded apace. Many changes were made, many innovations, particularly in the target design, and the manufacturing of those targets was made over the next few years. And then something very interesting happened. in the 2020 regime. We made some changes that started getting us into a much more interesting realm. 100 kilojoules. That's starting to feel better. We've got 3 significant digits now. And 150 kilojoules, 175 kilojoules. So now we're starting to feel like there's some momentum. And the thing about this process is when you get it to go, it goes very quickly. So the yield can go up or down very quickly when you're close to the border. And then in August of 2021, we had the shot heard around the world. So we got 1.3 megajoules, which is a factor of 8 higher than we'd ever seen before, and a factor of 4 higher than was predicted. So this was a really amazing moment, and we were super not ready. We'd been talking about success for many decades, but we were definitely not ready. However, were able to use this to build confidence that we were very close. This is 0.7 target gain. So it was clear to us that we would be able to ignite a capsule on the laser. We had, once we had gotten this close, it was certainly going to be feasible. So very exciting, lots of press, lots of complicated dynamics in the team. I mean, this, over 6 decades, literally thousands of people across many institutions contributed to the learning that built this target and executed this experiment. And this is a very complicated community. I would call the ICF community the people equivalent of plasma. So it doesn't hold together very well, except under extreme pressure. But boy, when things start going well, that's a real great moment to lean in. Everyone really, gravitates to success like this. So it was very exciting. And then, can I have the next slide, please? Am I too dumb to operate the clicker? There we go. So we went off and started what we called a repeatability campaign. And I just want you to note that tall blade of grass, orange blade of grass, is the 210808 shot I told you was 1.3 megajoules. And the next ones were the repeats. So what I said about the physics changing very fast, that was proof positive. The team came back and showed me a slide and said, these are the results of the NIF variability campaign. And I said, we did demonstrate that the yield is highly variable. That's not what we set out to do. We set a goal, though, in that period of developing a robust target platform that would allow us to get over 1 megajoule routinely. And so after these repeat shots, we learned a lot about the fidelity of those targets and how precisely they needed to be built. That really was a key. And our laser scientists, who are also geniuses, were able to start turning the energy up a little bit on the laser. So we went from 1.8 megajoules to 1.9 to 2, and then ultimately we went a little bit over 2 to 2.15 megajoules. And lo and behold, on December 5th, we had a 3.15 megajoule yield shot. So, and we were ready this time because we knew it was coming. So this was the National Academy's benchmark, target gain greater than 1, and that's why this is ignition. I've had a long, sort of unproductive conversation with one of the scientists in the program, arguing about how it was really ignition before, because from a physics standpoint, which is all true, that's fine, but the National Academies get to decide what 60 Minutes calls ignition. So that's how that came to be. So this is the fundamental building block that we've been working for 60 years. So again, engineers, scientists, many institutions, national labs, academic partners, international partners, industry partners, all had to come together to make this possible and to perform so many miracles, it's hard to enumerate them all. So really quite an extraordinary accomplishment. The team came to me the next day. Well, first I get a text, well, it was a pretty good shot last night, So, okay, how good? Well, we think, maybe we got ignition. By mid-morning, like, I think we got 3 megajoules. Good grief. And they said, what should we do? I said, we are calling the Secretary of Energy, because this is a big deal. There's no question about what we should do here. So if we go to the next slide. We did, called the Secretary of Energy. It took us about a week. So the team spent a week. You have to do counting radioactive decays in some of the detectors, so that takes some time. You have to, get all the diagnostic data in, and, there's a lot of analysis work. We brought in a peer review team from outside to, red team the data before we said anything stupid publicly. And then we got the Secretary of Energy to make the announcement a week later on December 13th, which was just incredibly exciting. She was very excited. The administrator, the NNSA, the first NNSA lab director to be a woman, Jill Ruby, and the president's science advisor, Arati Prabhakar, who it turns out had been a summer student at Livermore in the laser program, which was the best unscripted moment of the whole thing. And Marv Adams, who was the diversity adder to our panel, who is the head of defense programs, as a professor at Texas A&M, and became a viral sensation. He did a great explanation of fusion. He had little show and tell things. And then he made a statement to the community, if you're wondering how to be a part of this amazing scientific enterprise, and he leaned in dramatically in that sort of Mississippi way he has, says, "We're hiring." And he got 6 million views on YouTube and a lot of resumes, it turns out. Then we did a technical panel, which is shown at the right, and I think the most important thing from this picture is look how young that crew of people is. So we've made another handoff to a next generation who's going to take this science forward. And it was really wonderful to see them all sitting up there talking about the incredible work they'd been doing and the teams they'd been leading and just the amount of pride that was present there. The other notable moment for me, so the gentleman at the podium is Mark Herman, who heads the program that owns inertial confinement fusion. And I introduced the panel, and I introduced Mark as longtime fusion guy, Mark Herman. So I wasn't listening to what I was saying, but we now have T-shirts, longtime fusion guy, longtime fusion gal. All right, I think I have one more slide. And then, it's very hard to explain, but it's very unusual for a national lab to get this much attention for something good. So we've kind of leaned in on that. And the kind of coverage we got is kind of remarkable. So we heard about the 60 Minutes piece. I saw Bill Nye, the science guy, on CNN explaining fusion right before we were scheduled to go out for our press conference. You've made it. We had these NPR guys who not only said lasers, they went, pew, pew, pew. We were on Colbert. We were on Saturday Night Live. They actually did a skit about their son, the fusion scientist. And Cecily Strong did a great explanation of fusion and 192 laser beams, the whole thing. It was pretty cool. And many reputable news publications also covered this great event. And it's been wonderful. It's a great moment for the science community. It's a great moment for the power of big science and teams and multidisciplinary approaches. It's a great moment for this community of national labs and academia and everyone. And it really was very heartening to me that people were so excited about it. So we gave these T-shirts out to every single person at the lab and every single person we met on the street and everybody we could find. And, every person at the lab wore their Ignition T-shirt because they were darn excited. I work in procurement, but I helped because I, contributed to this, which is a really wonderful thing. And I hope we can keep that spirit alive as we go forward. I got to do all sorts of interesting things in addition to 60 Minutes, which was a little scary because most national lab people who've been on 60 Minutes are sweating, not having a happy conversation. I got to go to Davos, to the World Economic Forum, and talk to the chairs of all these big corporations about fusion, which was super cool. And, I got to go to the State of the Union, which was pretty interesting. So really got to come here, which was terrifying. Which was terrifying. So what does this mean in context? So we produce 3 megajoules of fusion energy. It takes about 300 megajoules off the grid to produce 3 megajoules of fusion energy. NIF is not a power plant. NIF is a national security facility. It was built to create fusion ignition conditions to help us steward the nation's nuclear deterrent. That's why we have the facility. That's what we're doing. That said, an igniting capsule is the fundamental building block of an inertial fusion energy power plant. So Could you build a system that was efficient enough to generate net energy from wall plug? And the answer is maybe, right? NIF is very inefficient. The laser is about 1% or 2% efficient. You can build much more efficient laser systems. You can build much more powerful laser systems. So the NIF facility is 3 football fields in footprint and 10 stories tall at its largest extent. That's how you make the energy to drive that little tiny capsule. Well, that's 80s laser technology. So there have been 3 revolutions in laser technology since then. You have to do it 10 times a second, not 1 time a week or 1 time a year, depending upon which year you look at. And so can you do that? We can certainly build the lasers that can do that, but can we build the infrastructure that allows you to manage an igniting target 10 times a second? Can you manage tritium? Because you're going to have to recycle it. You're going to have to capture it and recycle it and manage it. Can you build the blanket materials that'll capture all those neutrons and help you turn that into heat that can make power? So all of these things are technically feasible, but not without a massive effort, a massive investment, a really focused program to take this forward. But the opportunity is very real. So this administration launched a bold decadal vision for fusion energy. The initial investment in terms of dollars in the bold decadal vision was $50 million. And $50 million is not going to get you fusion energy in a decade. I just heard this week that we've launched officially an inertial fusion energy program at DOE. The initial investment in that program is $10 million. Again, it's not zero, which is super exciting, but there's a long way to go. And it's not just venture capital. So if you follow the fusion industry, between magnetic fusion and inertial fusion energy, there's about $5 billion in capital in private sector companies that have technology approaches that they think will generate a demonstration fusion power plant. Some are more plausible than others. Some have pretty advanced technology ideas. But even they're relying on public funding, because I have a big material science department that can help them solve problems like first wall materials, right? They don't have that. They don't have big facilities that will allow them to test how materials survive in radiation environments. They don't have tritium facilities. I mean, they don't have a lot of the infrastructure that really is resident in the national labs. So that patient public funding is critically important. NIF was near death numerous times over its history. We had great support in Congress that saved it again and again and again because people really believed in the promise of what this facility could do. And I think we've exceeded the expectations of many, including the many naysayers in the community who thought it just was not possible. I mean, the projections were that it would take 5 to 10 megajoules to ignite a capsule. So that was wrong. We're very proud of that. And many of those people actually apologized. They came back and admitted they were wrong, which is something else I love about science. When the facts on the ground change, people adapt and they internalize that. So that's been pretty fun. And there's a little bit of schadenfreude in that, but I told the team, no neener. I just can't do that. This is a moment to bring people together, not be a plasma. So the opportunity is very real, and I feel like my job for the last 3 months has been to be realistic with people. This is not going to happen without a massive effort. It's enormously difficult, and it's not just engineering. There's still physics to be learned and much work to be done. But if you go into our universities and talk to people about the possibilities of this technology, there are amazing students coming out of school today who want to be a part of this. So if we can capture that intellectual capital in this great moment where everyone is really feeling the power of science, that would be amazing.